Anyway, so okay, you can hear me now. Back home, if a couple of you say "yup" or raise your hand, that's fine. Uh-oh. Yeah. Okay. Okay. Thank you. So the next thing that I was, so we talked about angle of elevation, right? That's so when word problems, angle of elevation will show up from time to time. And so what it measures the horizontal and the line of sight looking up. So you're looking at a bird, at a plane, at a kite, at a tree, you name it, right? It will look like this. If it's angle of depression, it is the angle measured between the horizontal and the line of sight going down. Okay? Thank you for those of you who replied. Appreciate it. Horizontal going down. Okay? That's what you need to remember if it's angle of depression. So, there it is. Let's draw our scenario here. So there's a horizon here, horizontal. And here you have to pretend, let's give you a scenario here. Imagine this is like the surface of the water, right? And we just consider that a straight line, even though it's never still, right? And let's say you're a boat and you spot, a broken, you spot, let's say somebody lost their anchor down here, right? And so you'd be looking down at a certain, and so this should be dashed technically, right? So let's make it dashed so you understand that that's the line of sight, right? So the angle created between the horizontal and the line of sight looking down is called the angle of depression, and that will be a number eventually, okay? Angle of depression, there it is. So triangle will look like this. Okay, so basically, if you notice an angle of depression, your triangle, because there's now a depth or the height of the triangle, right, as well, which is not mentioned, but it is there. So it will look like this, or it will look like this. Oh, same triangle. It must be Friday. Is it Friday? I guess I just wanted to show you that sometimes you have to start all over again, okay? And so imagine this, you're flying a plane, you're up here, right? There is a horizontal, like straight ahead of you, that's like your path, but you're looking down at the airport. The airport is down here. This would be considered the angle of depression. So we're gonna mark it like this. So how are we gonna do this? Down like this, and down like this. Angle of depression. And so these are the most common terms that you will be, I think I will give you that one diagram that I like that one because it kind of shows you both at the same time, okay? So make sure you write that down. And once you've done that, I will give you another diagram. Uh, what? What? Yeah. I was just thinking we're gonna do a problem soon, so but if you rush, you'll get back in time. All right, backside. So imagine there's like a cliff here, right? And then there's the ground here, or there's water down here. Let's say this is the cliff, and so you're standing here at the edge, just enjoying a nice sunset, right? I don't know why you would have your arms up like that, but hey, it is what it is. So this is the horizontal here, right? And then, so let's imagine that there's a bird up here, and down here there's a boat. It could be anywhere here. So let's draw a boat as best you can, right? That's my version of a boat. And so if you look up at the bird, you've now created an angle of elevation. If you're looking down at the boat, right, that's considered angle of depression. So both of them are present in one picture here. So this is the angle of depression, and this is the angle of elevation. Okay, so there you have it in one picture here, and they could now ask you like what's the depth of, you know, how far below is the boat from you, or how high up above the level ground is the bird, or something like that. They could ask you questions like that. Okay, so keep that in mind. I think that is it for terms. If there are any more, then I will present them to you and talk about them as we go along. Okay, so let's try an example here. The angle of elevation of Sandra's kite string is 70 degrees. If she has let out 55 feet of string, calculate how high, calculate the height, sorry, calculate the height of the kite. So the angle of elevation of Sandra's kite string is 70 degrees. If she has let out 55 feet of string, calculate the height of the kite. So right away, if you see angle of elevation, right, if you see this word, these three words, I guess, combined, you should be thinking, right, that your triangle will either look like this or it will look like this. So you're basically making a ramp with the two of them, right? Think of a ramp, right? Up, down, but this is one of these two scenarios. One of these two scenarios is what you're thinking of. Okay, so that helps you. Oh man, it's out again. teachers are now doing everything online as well. So I feel like it's overloading or overwhelming our system. And as well, I have more of you online than here, right? So that might also be the case. Anyway, so the angle of elevation of Sandra's kite string is 70 degrees. If she has let out 55 feet of string, calculate the height of the kite above ground, that is. So you have to imagine. Okay. Do you have a question, Francis? Or oh, I need to redo the presentation. Yeah. Thank you. It's frustrating. Thank you for your patience, folks. Just hold on there. Can you see it now? Doesn't seem like it. No. Now, yes. Okay. Joshua and whoever else, can you see it now? Junior or Bella? Okay, good. Let's see if we can do at least one example here. Okay. So in this case, you have to imagine, right, the kite being up here perhaps. And so you kind of imagine the horizontal going this way and the line of sight. In this case, it's the string, right, attached to the kite. So if you want to draw your kite here, you can. So the string is being let out, attached to the kite, and so there's a height here, right? So where do we put the information? Well, the 70 degree is your angle of elevation, which makes sense, right? It measures the opening between the ground and the string. Okay, and it says that she lets out 55 feet of string. So this is your string. So the 55 feet would go right here. Okay, and then they're going to ask you for one of the two sides that remains. So calculate the height of the kite. So this would be the height. So what that would be our unknown there. So this is the diagram, right? And now we're going to solve. So same as before. If this is your angle, you travel out. What do we call this? Opposite. Across from the 90 is your hypotenuse. We don't care about the adjacent. So just quickly, I'm going to write this out for myself. SOHCAHTOA, right? So it's O and H. So we're going to use SO, right? So sine of 70, that's what S stands for, right? Sine of 70 degrees. Remember, it's always attached to an angle. Will be opposite, which is X, over hypotenuse, which is 55. Put a 1 there. You cross multiply and divide. So X is essentially 55 times sine of 70 divided by 1, which you don't need to do. So let's go ahead and go 55 times sine of 70. That is 51.68 feet. And that's how high above the ground the kite goes, right? What about one that doesn't have Okay, here we go. One that doesn't have angle of elevation. Okay, so write this down. Brad is building a ramp. The ramp must form an angle of 22 degrees with the ground. And okay. Oh yeah, enjoy it. Take care, man. Did you have issues with your connection as well?
With that?
Yeah, was it disconnecting sometimes?
I didn't have that problem.
Okay.
You have not right now?
I had it a couple of times, yeah.
No, I had that weeks ago.
Okay. Take care. Yeah. 22 with the ground and reach a point. My good friend, Mr. Hudson. You might have him in grade 11, who knows? 1.5. You should try to get in with him because he's retiring after this year, unfortunately for me. 1.5 meters above ground. Determine, I'm going to scroll up a bit, okay? Determine the length of the ramp. Okay, I want you to, if you're uncomfortable doing this in your notes, grab a piece of scrap paper. Try to see if you could graph this triangle, if you could make a diagram and put the information where it's supposed to go, as well as having an X on the side that they're trying to get you to solve. Okay, so I'm going to pause the recording here. Okay, so now we have the scenario, and it says that it's a ramp. So a ramp either goes up like this, or it could go down like that, right? It's up to you from which side you want to approach. I usually go from left to right. So there's my ramp. This is the ground here. The ground and the height of the ramp make a 90 always, right? It says that the ramp must form an angle of 22 degrees with the ground. So the ramp and the ground must form, they make an angle of 22 degrees. Okay? So that's established. It says, and reach a point that is 1.5 meters above ground. So the ramp needs to reach a point, which for us is here, so that the height of it is 1.5. So 1.5 meters goes outside. That's a side length. The 22 degrees should never be outside in any way, shape, or form. The degree is always between two sides. So it's either here or it's up here. This is your 90, right? So you need to decide where it makes sense for it to go. They could have also called this angle of elevation. They could have said the angle of elevation of the ramp is 22 degrees. It's saying the same thing, okay? Now it's the 1.5, so they want us to find the length of the actual ramp. So here it is. You label. There's the angle, the reference angle, so it's opposite hypotenuse. That is definitely so, right? So it's this one, sine of 22 degrees is equal to opposite, which is 1.5, and hypotenuse is x. You put the 1 here to help you see that you're going to have to multiply down and divide up. So it's really 1.5 divided by sine of 22. And x is going to be the ramp, right? If you want to write down ramp instead of x, that's fine. So 1.5 divided by sine of 22, that's 4.004. So we're just going to leave it like that. And we are in meters. There it is. That's the length of the ramp. We're going to keep going. Make sure you have that written down, okay? I think it was Carter, right? Carter, you told me you were here. Okay, let's keep going. Another word problem for you. Got it? Okay, ready to copy? Here. How far from the base of a flagpole must a guy wire be fixed if the wire is 12 meters long and makes an angle of 63 degrees with the ground. Question mark. Okay, scrap paper, try to sketch it. I will write another one down already. Oh, there's that. Try to graph that. All right, I don't know how you did, but here we go. So it's best to read it all at least once if not twice. Okay, how far from the base of the flagpole must a guy wire be fixed if the wire is 12 meters long and makes an angle of 63 degrees with the ground? Now, going back to Pythagorean theorem, if you see a guy wire, you know what it is. You know that it, right? If you have your pole, hydro pole, whatever it is, fence post, a guy wire helps stabilize a pole, right? Sometimes this post would be pulled too far this way, so you have to have a guy wire pulling it that way to make it stay in line, right, and straight. So you know a guy wire, you can kind of imagine, right? The flagpole is here, right? And the guy wire will be attached like that and anchored to the ground. Okay, so this is the ground here. Okay, so you know that the flagpole makes the 90. This is your guy wire. It says that uh, the guy wire makes an angle of 63 degrees with the ground. So the 63 goes here. Okay, and it says that the wire is 12 meters long. So this is 12 meters. Where would you put the X? That's the big question. Where would you put the X? Where would you put the X on this? Base. All right. I get people saying that it should be going here. Okay. And that is correct. It says how far from the base should it be fixed. So we're talking here, right? It could have said how high up the pole does it need to be attached. The same question could be asking for this stretch here, right? Just by changing a few words. Anyways, let's label. This would be opposite. I don't care about it. Hypotenuse, adjacent. A and H. So I know you're going to find this extremely annoying that I do this all the time, but I see it all, guys. And so this is, if you write this down, it's going to help you. So we need to use cosine because A and H, right? Cosine of what? 12. Nah, 63. Yes, right? So it has to be the angle. I do see the cosine of 12 from time to time, right? It's not a degree, you can't do it. Shouldn't be there. And the order matters. Adjacent is x, hypotenuse is 12. It's in that order which you need to place them in. So you're going to have to multiply and divide by 1, which is irrelevant, right? So we're just going to go 12 times cosine of 63. And that is 5.44 or 45, sorry, meters. That's how far away from the base of the ladder, right? That's how far you'd have to go to make that, to affix it to the ground, to anchor it. There's another one. So tomorrow you can be guaranteed an AC on word problems, all right? Write it down, then make a diagram before we continue, okay? Recording. Again, I hope this makes sense, right? When you're reading this, Reba walks 25 yards across the diagonal of a rectangular field. If the angle between the width and the diagonal is 67 degrees, how wide is the field? So here we go. If this is your field, rectangular means it's longer than it is wide, right? Okay, we would consider this the length and we would consider the shorter side width. Diagonal means that you're either here and walk across the field this way, or you're here and you walk across this way. It doesn't really matter. So let's say that I'm going to make this dashed, okay? You're walking across like this from end to end, okay? That's the path that Reba's walking. And it's 25 yards across the diagonal. So this is 25 yards. Okay, this length is 25 yards. And this is where it gets a little tricky. It says, if the angle between the width and the diagonal is 67, how wide is the field? You're like, Mr. Dirksen, there's a width here and there's a width here. Which one is it? It's either one. You choose, right? So if this is the width and the diagonal, how about we choose this one? So this is 67 degrees right here. It's here or here. You choose. It's the same angle. They are the same, okay? But you can only work with one of these triangles, right? So it's asking us how wide the field is. So how about we take this one and just copy it out there. Doesn't take long. This is 67. This is 25 yards. They want us to find the width of it, which is this side right here. So that's what we end up with. It's a cutout of the original. So this is opposite. We don't label it, sorry. We don't care about it. Opposite, hypotenuse, adjacent. Yes, it's cosine. Right? So ka toa. You're gonna be so good at this by the time you leave grade 10. Your grade 11 teachers are gonna be like, what? Right? What happened? Cosine of 67 is adjacent, which is x, over hypotenuse, which is 25. And here you just multiply, right? Multiply, divide by 1, irrelevant. 25 times cosine. I didn't pick this one right. I shouldn't have so many cosines back to back. But it is what it is. And that is 9.77. And we are yards. They could have asked you how long, right? How long is the field? Right? If they had asked you for the length of the field, how would this have changed? Well, the x would have been out here, right? Asking for the length. That would have been a sine situation, right? So keep that in mind. I think I'm going to call it quits here, but be ready for a word problem tomorrow. And that is everything for now. Okay, so take care. See you tomorrow.